All right. Thanks everyone for coming. I'm Erik, and today we're going to talk a bit about the G1 garbage collector in JDK 9. But before we begin, I would just like to show you all this slide and let it hang out there for a few awkward seconds for all of you to enjoy. And now that's out of the way, let's look at today's agenda. We're going to be talking about the G1 garbage collector, and first of all, we're going to start off with a quick intro into G1 in 2017. We will then continue on looking at 5 major improvements to G1 since JDK 8. And then last but not the least, we will do a little bit of sneak peek into the future and see what's coming up for G1. But who am I? I'm Erik. I like to program garbage collectors. I work at Oracle in the JVM GC team and has done so for about 6 years now. The past 3 years, I worked on the G1 garbage collector, and I'm also a reviewer in OpenJDK, where I contributed a lot. So, a quick intro into G1 in 2017. First of all, what is garbage collector and what is G1 solving? Well, garbage collection is a way to manage memory. So in Java, programmers do not need to explicitly manage the memory themselves. You will allocate your objects with new, and then the memory will be reclaimed by the garbage collector once it's no longer in use. You can compare this to C, where programmers must manage the memory themselves using malloc and free. How does garbage collection work? Well, all your objects will be allocated in a memory area called the heap. These objects will be laid out in memory with their respective fields. Those fields can in turn contain references to other objects, but also ints and booleans and other values. As you allocate more and more objects, you will start to fill up this memory area called the heap. And once it's completely filled up, well, there's no space to allocate more objects in, so something has going to have to happen now if the program is going to continue running. What is going to happen is that the garbage collector will pause your application, and then it will see which objects are currently in use by the program. Because if you think about when you write a method in Java, you might allocate a bunch of objects, do some computation, and then return a result. But those objects you use for a computation, you don't really need them anymore. So the garbage collector will find out which objects are in use, and it will do so by starting from the so-called roots. So in order to figure out which objects are live and the heap and being in use by the programs, you stop the Java application, you scan the thread stacks for the Java threads, you find the references pointing out objects like this, and then you say that, now I found those objects, I'm going to consider them live. But as you see on the slide here, there's a bunch more objects, and we can iterate over the fields in each object in turn and follow the references. And then we will find more objects that are reachable from the roots. And if we keep doing this and iterate on this algorithm, we will sooner or later find them all. Once we have found those objects, we can compact them to one end of the heap. There are other schemes available for memory management, but this is one example. The objects can be compacted to one end of the heap, and we will now have a contiguous free memory area that we can use for new allocations. The program can then resume running, and suddenly there's more space for new objects to be allocated in. G1 is one such garbage collection algorithm, and this is the first page of the original paper, which is getting a little bit old by now. So the paper was published in 2004 on the G1 garbage collector. The JDK got experimental support for G1 in 6U14 and official support in JDK 7U4 in 2012. And this year, a few weeks ago, when JDK 9 was released, G1 became the default collector for the JDK. So with this information, be wary when you're reading old blog posts, Stack Overflow answers, etc. about G1, because quite a bit has changed between 2009 and 2017. The G1 has evolved a lot since it was first introduced with experimental support. So the goal of G1 is to provide both throughput and low latency. And throughput, you can think of that as roughly the number of transactions per second, or the total running time of a program, whereas latency, that will more correspond to the maximum time of a transaction. And the default pause goal for G1 is 200 milliseconds. This pause goal can be tuned. You can say to G1, I'm okay with longer pauses, which probably will result, if you have a backend service, for example, in longer request times. But in turn, you will get better throughput and get more work done per time unit. Whereas if you are concerned about latency and say that, I don't want it to pause not at all or very little, you can decrease this value to a much lower value, but there's always a trade-off, so here you're going to have to sacrifice throughput a bit. But in turn, you will get shorter pauses. So how does G1 achieve this? Well, the goal here is, or the method here is to use generational region-based memory management. That's quite a term. So the heap is split into multiple regions. So the region size will depend on the heap size. For example, if you have a 4 gigabyte heap, then G1 will divide it into 2048 2 megabyte regions. New objects are allocated into so-called Eden regions. And a young collection will happen after a number of Eden regions have been allocated. During such a young collection, G1 will find live objects in those Eden regions and compactly copy them into a survivor region. Objects will then continue to be allocated in Eden regions, and after a while, if an object survives multiple young collections, they are compactly copied into an old region. So as your program keeps running, more and more Eden regions will be used for allocations, young collections will happen, the objects will be surviving and moving into survival regions, some will survive for longer times, filling up more and more old regions with live objects. And sooner rather than later, G1 will have to start a concurrent mark cycle to find out in the old regions which objects are actually in use and which aren't. So the Java application is not stopped during this time. The concurrent mark will be running alongside your Java application, traversing the heap and finding all these live objects in the old regions. Then, once the concurrent marking cycle is finished, Eden, survivor, and old regions are collected in so-called mixed collections. The live objects are again compactly copied into survivor and old regions. So on the slide here in this example, we have taken all of the Eden and survivor regions, which must be collected every time, and also chosen 2 old regions to collect. The result is, as time goes on, G1 will collect more and more of the old regions, so more and more of the heap will become free. And then, once there no longer are any old regions suitable for collection, for example, they might contain too many live objects, so it's not worth collecting them, G1 will once again resume doing young collections. Thus, G1 moves and transitions between the following states. It starts out by doing young collections, which will copy objects into survivor regions and promote them to old regions. After a while, as the heap is getting more and more full, a concurrent mark cycle will be started. The concurrent mark cycle is not only running concurrently with your application, there can also happen young collections during the concurrent mark cycle is running. Once the concurrent mark finishes, G1 transitions over into doing mixed collections, and once there are no longer any suitable regions to collect, it will once again transition back to doing young collections, and so the cycle repeats. So, with that bit of knowledge about how G1 works, we're going to look at 5 major improvements and how they were done that has happened since JDK 8. So, we're going to have a look at stringed application introduced in 8U20. We're going to see class unloading with concurrent marks, which shipped in 8U40. We're going to see the eagerly reclamation of humongous regions introduced in 8U60. And then the adaptive start of the concurrent mark cycle. This is shipped in JDK 9 just recently. And also a bit about more efficient collections that were also shipped in JDK 9. But let's start out with stringed application. So in this example, we are allocating 2 strings. I have one named conf, one named J1, Java for Java 1, and they have very similar content. If you look at the slide, they actually are identical. And now you might think a little bit, couldn't we make better use of the memory instead of having these duplicated character arrays on the heap taking up valuable space? Could we do this? Would that be okay? Or could there be any problems with the Java program if we were to do this little trick? It is actually perfectly legal and valid and fine, because in Java line string, the character array value is both private and final. So if we do this behind the scenes, your Java program will not notice any difference. The way we do this is that during a collection, G1 adds all newly allocated strings to a queue. And then after the young collection is done, G1 will concurrently check if any two strings equals. If the two strings are identical, then you can make them refer, or G1 makes them refer to the same character array. And please note, this is not the same thing as intern strings. String intern cares about string objects, whereas string duplication cares about the character arrays or the value fields. And internally in the JVM, they use different tables. This can save a lot of memory and a lot of footprint on the heap, depending on your application, of course. If you have maybe a lot of SQL statements that are repeated that contains the same values, this can be a big memory saver. The trade-off is that it will use slightly more CPU due to the concurrent work going on at the same time, and it might also cause slightly just a bit longer John collections. So if it's worth it or not, that depends on your application, how much memory you save, and your CPU requirements. You can try this out with the use string duplication in JDK 8U20 and later. The next improvement we're going to look at is class unloading with concurrent mark. And this is a tricky subject. So objects on the heap have a corresponding class, and those classes have in turn been loaded by a class loader. When all instances of a class on the heap are dead, that means that the class itself is dead. And if all classes loaded by the same class loader are dead, that means that we can unload these classes and garbage collect the corresponding class loader. Now the question is, how do we find out if a class is dead or not? Well, G1 will traverse the entire heap, and as it does so, finding live objects, it will encounter live objects and can therefore, from those live objects, find out which class they belong to, or are instances of, and mark that corresponding class as live. Since a class can only be unloaded if all classes loaded by that class loader are dead, we will mark the class loader as live and all classes loaded by that class loader as live. As G1 traverses the heap more and finds more and more live objects, more and more classes will be marked as live and the corresponding class loaders. After the heap has been iterated through and we found all live objects, we can in turn iterate through the class loader graph and find out, there's a class loader that isn't marked as live. That means that class loader is dead, and we can unload all the classes that class loader has loaded. So in one tricky sentence, after all objects have been visited, then unload all classes loaded by class loaders that aren't live. And there are two algorithms in G1 that visits all live objects on the heap. You have the concurrent marking, which is it's rather tricky to find out the live classes during current marking, but it performs pretty well. And then we also have the fallback full garbage collection. Here it's a lot easier to find out which classes are live, but it's slow and will cause longer pauses. So in JDK 8U40, we finally shipped class unloading after concurrent marking. This is controlled by the flag class unloading with concurrent mark, and it's enabled by default since 8U40. And it can reduce the need for full GCs quite a lot in your application if you load and unload a lot of classes. And again, available in 8U40 and later. The next little trick or improvement or feature we've done is, well, we've done many, but one significant is eagerly reclamation or eagerly reclaim of humongous regions, and this was shipped in 8U60. So let's have a look at that one. When objects are larger than half a region, they are called humongous in G1. And the regions they are allocated in are called humongous regions. G1 doesn't copy humongous objects around on the heap because it's too expensive. They are larger than half a region, so they take up a lot of memory. So thereby copying them takes a lot of time, something we do not want to do. But on the other hand, these objects use a lot of memory, and if they become dead, we want to free that up pretty quickly so we can reuse it for other objects and allocations. So what we do is that we utilize the fact that G1 keeps track of references between old regions, as can be seen on the slide here. We have a couple of old regions and one humongous region. We see that there are no incoming references to that one humongous object in the humongous region, and there is one outgoing references from that humongous object. But since there are no incoming references from other objects in old regions, that means that the only thing that can keep this humongous object alive is an object in a young region, that is either Eden region or survivor region. But remember, when we do a young collection, we will look at all the live objects in all the young regions. So during the young collection, G1 will check if there are any references from a young object to this humongous object. If no references are found from young objects, we know that nothing is holding on to this humongous object. We can reclaim the memory and reuse it later. So G1 can, due to this feature, reclaim humongous objects during a young collection. It does not need to wait for concurrent mark to finish to realize that the object is dead. This was introduced in 8U60 and can help quite a lot if you allocate a lot of large objects. So the next feature we're going to look at is the adaptive start of concurrent mark, and this was shipped in JDK 9. So this concurrent mark cycle that looks through all the live objects in all the old regions, again, it can take a little bit of time until it finishes. But it's important that it does finish, because if it doesn't finish, then G1 doesn't have the liveness information needed to collect the objects in the old regions. So concurrent marking must finish before the heap is full with the old regions. And the problem is then, of course, when should it be started? Prior to JDK 9, you had to use the flag initiating heap occupancy %, which meant that you set a value, for example, 35, and concurrent marking would be started when the heap was 35% full. Now, this is obviously a static way to do this, and many of you experience problems with this, that the concurrent mark cycle was kicked off too early, resulting in slightly worse performance, or too late, resulting that we couldn't collect the old regions. So in 9, we replaced this with a much more adaptive dynamic calculation. We do use for the first collections just as an initial value to the ergonomics engine, the value of this flag, and then we sample runtime data and see how your application's allocation performs and how much data you allocate, and then we can use those samples and the feedback from previous concurrent mark cycles to determine when to start off the next one. And of course, we always add a safety margin because we really wanted to finish in time. So this results in much less concurrent mark failures, which in turn saves you from a lot of these fallback full GCs. This is controlled with the flag -XX G1 use adaptive IHOP, and this is enabled by default in JDK 9, and I recommend you to keep it on. So let's look a bit at the new, more efficient collections that we have introduced in JDK 9. We did a lot of work going into JDK 9. In fact, we had more than 250 enhancements going in for G1. There are things all over the place. There are more parallel phases. There's improved plab sizing, parallel freeing. We have tlab resizing, concurrent mark from rows, and a bunch more updates to the internal data structures for the garbage collector. We have more than 180 bug fixes going into the G1 GC in JDK 9. So what is the effect of all of this? How much did we actually improve? Well, the uptake has actually been great. Here I had a bunch of nice logos and quotes from various things, and then I piped the slides through legal, and out came this slide. So G1 has been picked up by major Java frameworks and applications, especially GUI applications, such as some very well-known IDEs, and also server-side frameworks. So many major companies have also switched or are switching to G1 for their workloads, particularly those where they care about the pause times, but also cares about the throughput and need a mix of those. And remember to always run with the latest JDK release if you are running with G1, because the improvements are being kept added, so you want to ensure to get the best performance that you are running with the latest version. So let's look a little bit into the future of G1 and what is going on at the moment. We are not idly sitting by. We are continuing improving and developing, even though 9 is just released. So for the next JDK release, we are looking forward to parallel fallback full GC. So the reason that all of you has had problems with the fallback, which is the full GC is not supposed to happen with G1, but if it does happen, it has been really painful in the past. So for the next JDK release, we are looking forward to parallel fallback full GCs, that even though it is a failure case, you will have a much faster and speedier recovery. This is being reviewed right now on the mailing lists, and you can see more details in JEP 307 on openjdk.java.net/JEPs/307. We have also made significant improvements to the card scanning. So card scanning is an eternal detail of how G1 works, and it needs to perform quite a lot of it. So this summer we revamped the code and improved it quite a bit, which resulted in a nice boost and shorter pauses. But we do not stop there. We are continuing to push G1 further continuously. And at the moment, there are patches going on to rebuild the remember sets concurrently. We haven't looked into those today, but the remember sets are a key data structure into how G1 works. And in the future, we can hopefully rebuild them concurrently. We are also doing a lot of work into the ergonomics engine, trying to improve it and improve the ergonomics so you don't have to tune as much, but instead G1 can itself figure out what values to use and what flags to set. Now, if you all want to stay connected, and I hope you will, please join the community at hotspot-gc-use@openjdk.java.net. There are a lot of experienced users on that mailing list, including the GC developers. And to all you users who are on there helping each other, thank you. We really appreciate that you, the ones who tune a lot and have a lot of experience, help out the newcomers to the community and answer questions. We, the GC developers, also read this mailing list, but unfortunately, we don't always have time to answer. So again, thank you for those of you providing answers. You can also find us using IAM on OpenJDK channel on irc.oftc.net, where you can chat with us if you have any questions. We are usually around. And lastly but not least, you can find me and several others of the JDK and JVM developers in the DevOps corner in the Oracle Developer Lounge here in Moscone West. You can learn more about the work going into G1 at openjdk.java.net and learn more about Worker and Java at worker.com/java. If you're on Twitter, please follow at OpenJDK or at Worker and the hashtags Java1 and DevOps. And with that, I would like to say thank you and leave plenty of time to questions. So, yeah, question over there?
Any information about performance benchmark numbers?
No, the question is, I'm going to repeat it for the video. Do I have any performance numbers that I can share with you or benchmarks result? And no, I don't have anyone I can share with you on the slides today, unfortunately. But please try it out and see how it performs. I think you will be hopefully satisfied. Yeah, question over there? Sorry, come again, please?
How big are those regions?
Yeah, so the question is, how big are those regions? A region can be anywhere from 1 megabyte to 32 megabyte. It depends on you can set it yourself with -XX G1 heap region size, but I would probably recommend to let you leave G1 to select appropriate size of the region. It will look at the heap size in total and then decide. But if you are having problems with, for example, humongous allocations and humongous objects, then you might want to bump it up a bit. Yeah, question again over there?
If an object is bigger than the region size,
Yeah.
how is it?
So the question is, if an object is bigger than the region size, I said that the regions might be as small as 1 megabyte. What if you allocate, for example, a 1.5 megabyte byte array for some, I don't know, image data or something? Well, when G1 allocates then a humongous region, and a humongous region can span multiple regions, so the object will be consecutively laid out in multiple humongous regions, in this case 2 if you have a 1.5 megabyte allocation and 1 megabyte regions. But it will still be the only object in those 2 regions, which will be next to each other. Yeah, question in the back? So the question is this feature string application that was released in 8U20 on by default? No, it is not on by default, since there is a little cost in terms of CPU, both with the concurrent work and also with the work during the pause. We have it off by default, so you can opt into it. Yeah, question in the front there?
There are objects being copied from one region to another. How you're making sure that this object is not being modified by this at the same time?
Oh, so the question is, yeah, I get the questions. So if the question is, if an object is copied from one region to another region, how do we make sure that no Java threads or your program is modifying the object at the same time? The application is stopped the JVM can stop the Java application, which you will not notice besides GC pause in the log. But the application is stopped, so no work from your application is ongoing at the same time as the object is copied. Yeah, question in the front here?
So for YAP collection, is there any option similar to concurrent marking?
So the question is, for Young collections, are there any options similar to concurrent marking? Do you mean, for example, to concurrently find the live objects in Young regions? Yeah, so can G1 concurrently find the live objects in Young regions? No, it can't. It will stop the world. But this is based on the hypothesis, which is very, very often true, that for Java, most objects are allocated either die young or they live for a very long time. So even though you will fill up the Eden regions with quite a few objects, when we stop, we only have to care about the live objects. And those are usually much, much, much fewer than the total number of objects that have been allocated. So therefore, we don't have such a problem with too long Young collections. Yep, question over there? So the question is, have you thought about maybe using some kind of Java annotations to provide hints? Yeah. You mean hints for a particular class? Yeah, no, we have not given that too much thought, and I don't think there's that much we can use from such hints. We are usually fine by figuring that out in the JVM itself. So no, we have not thought about it, but we might do, but I don't think there's too much value we can get out from that. I think there was another question maybe in the back. Yeah, question over there.
Do you foresee any other big improvements coming up for G1?
Do I foresee any other big improvements coming up to G1? I actually do think that the ones we had up here on the slides might of course differ between you and me, but these are, to me, pretty big improvements, and also the ones we are looking into, rebuilding the memory sets and improved ergonomics, will also hopefully result in big improvements. So to me, these are big. To you, I don't know.
They seem to be big, but I'm wondering, so G1 started in 2007.
Yep.
Is there anything now that is similar to that is still in its early ages, maybe in the research part of development?
Yeah.
The future will revolutionize garbage collection.
Yeah, are we doing any research that will revolutionize GC? Well, I think about GC like 300 days a year. So yeah, we do think a lot about it. I don't want to stand up here speculating what goes in and what goes not in, but yeah, there's a lot of activity that we're doing. So hopefully that will result in some nice improvements. It doesn't always do that, unfortunately, but a lot of the time we can make some pretty good improvements, and we will continue to do so. Yeah, question over there?
Any data into how much does the concurrent marker reduce the full GC impact on the whole gen?
Yeah, so the question is, how much does the concurrent mark reduce the need for, or the time for a full GC? So G1 doesn't use full GC in its normal operation. As we saw on the slides, G1 prefers to move between Young collections and then transition to Young collections and concurrent mark, and then transition into mixed collections instead. So it will collect the old regions incrementally over a number of mixed collections, and preferably don't have to do a full collection at all. Which means in lot smaller pause times compared to a full collection. So hopefully with concurrent marking and the mixed collections, you can avoid full GCs completely and don't have to have them at all.